Hello and welcome everyone to my presentation. My name is Frederik Zahn. I'm with the Institute for Automation and Applied Informatics at Karlsruhe Institute of Technology, and I'm going to present you joint work with Mr. Hagenmeier on modeling power systems as flat hybrid automata for controlled line switching. When we imagine the future power system, we generally think of a system which is smart, which consists of a lot of connected and communicating devices with largely digital automation and a lot of data and data-driven methods. On the other hand, a power system always is a physical system with complex dynamics and a lot of control loops in order to ensure proper operation of the system. In order to engineer the modern power system, we will need models and tools that are able to integrate the state-of-the-art algorithms and methods into the physical domain of the real grid. One interesting case is the case of line switching in power systems. Line switching basically means that a transmission line in the system is activated or deactivated. This allows to adapt the topology of the grid for specific production or load scenarios. Specifically, the operation of the power system can become more or less efficient by activating or deactivating lines. That more lines don't mean necessarily more efficient operation is known as Brass paradox. Other reasons for deactivating or activating lines is maintenance or faults. In the literature, there are mainly two lines of investigation concerning line switching in power systems. One line treats the optimal grid topology, known as optimal transmission switching or OTS. This line of research investigates optimization problems to find optimal topologies. On the other hand, we have dynamic considerations about stability of switching. This line mainly is concerned with faults and putting lines back into action after faults and investigating the stability of the system before and after. In practice, line switching often is done by opening or closing the switches of the line under load. This causes oscillations and discontinuities in the grid. A system operator would do the following steps. First, lines or a line is chosen that is to be open or closed. Then calculations are done to assess the stability before and after the switching, and if the system remains stable, then the switching is applied to the grid, and the grid is left to control itself to a new equilibrium. Our idea now is to change that. We want to investigate methods how we can automate line switching and make it a smooth transition without oscillations or jumps. We therefore need a few ingredients. First, we need a good model that can integrate the dynamics, the discrete and the continuous parts. We then need some methods for automated planning of switching, and we need an application layer to apply our method to the grid. In the present note, we investigated the modeling part and we showed how manual planning can be done for the switching on a small example. The example that we looked at is a very small 3-bus with 3 buses and 3 lines. We made the assumptions that the lines are lossless, that the generators have second-order dynamics, that voltages are constant, which means that we don't have to take into account reactive power, but we only can look at active power, and that the lines are unconstrained. We further assumed that the buses are controllable, which is a common assumption in the microgrid literature. This is achieved by stating that at every bus we have a generator and a load, but we also have some type of storage to balance the output of the bus. In our case, we just assumed a battery, but we didn't model the dynamics of the battery. This leads to very simple equations. On the left hand, we have the generator dynamics. In the middle we have the power transmission between buses, which is parameterized by B, which is the line susceptance. And we have the net bus power. The deltas are the angles of the generators at every bus. In order now to integrate the discrete dynamics in our model, we use a flat hybrid automaton approach. Flat hybrid automata have basically the same structure as normal hybrid automata. We have a discrete part which consists of discrete states, switching sets and transitions, and discrete inputs. On the whole, this forms an automaton graph. On the other hand, in every discrete state we have continuous inputs and continuous dynamics, which we have seen on the slide before. Flat hybrid automata have the particularity that the continuous dynamics are differentially flat, which we will discuss on the next slide, and that the automaton graph is fully connected. This, together with some other assumptions, leads to a completely controllable model. Going back to our example from before, we can now construct a flat hybrid automaton model. To this end, we choose 4 discrete states, each of which models a different configuration of the grid. D1 models the configuration that all lines are active. D2 to D4 models the different states where one line is deactivated. We do not consider multiple deactivated lines in this example. The deactivation of the line in terms of the dynamics is quite simple. Only the term for the transmission between the 2 buses is put to 0, which can be modeled by putting the susceptance B to 0. On the right, you see the automaton graph of this flat hybrid automaton. So deactivating or activating lines on the automaton level is simply modeled by transition between discrete states in the graph. The switching sets are chosen to be equal angles, which I will come back to. This allows for smooth switching and only for smooth switching. The dynamic equations in each discrete state are differentially flat, which is a basis of the flat hybrid automaton. This allows to reformulate the dynamic equations in a way that the input is on one side and that the states are on the other side. So by constructing trajectories for the states, which are the phase angles and their derivatives, we can directly calculate inputs to realize the trajectories. For more details on differential flatness, we refer to our paper. If we now want to plan a trajectory for smooth line switching, we have to define a scenario. In our case, we want to open the line between buses 1 and 2. Therefore, we have to control the phase angles of buses 1 and 2 to the same value. If we do so and we then put B12 to 0, which effectively models the switching, there's no jump in the other phase angles. We decide to put both angles to 0 for simplicity, but they could be put to any value as long as delta 1 equals delta 2. So we start from fixed bus powers for all buses. We then control the phase angles of 1 and 2 to 0. We open the line and we control the system back to the fixed bus powers from the beginning. We can do so by just defining trajectories for the phase angles and directly calculating the inputs, which are the net powers at the buses P1 to P3. We choose a polynomial ansatz of 4th order, which allows for a smooth and differentiable function, and which is quite simple to compute. In the results, we see that the phase angles 1 and 2, which are in the upper plot, the blue and the green dashed line, reach 0 at time 2.5, and the switching is denoted by the gray dashed line. As we see, there are no discontinuities and no oscillations in the phase angles, in the bus power or in the line power. In the plot in the middle, we see the bus power and we see that in the beginning we have the fixed powers and in the end we arrive at the fixed powers again, so putting the system to the same state as before. Only the line powers and the angles change between the initial state and the final state. In my talk, I have shown how modeling line switching as flat hybrid automata is possible, and how from this we can construct smooth switching without jumps or oscillations. I also have shown how to implement it for a 3-bus network as a proof of concept. In future work, we want to look at larger grids with more complex dynamics. We also try to optimize the trajectories for less electricity consumption, and in the end, we want to integrate the whole framework for automated trajectory planning. Thank you for your attention.